Yes, good evening once again. So we start our discussion on ANOVA last week. We have gone through some basic concepts. So we have done something and found out that we said that whenever ANOVA is an omnibus test, it tests whether there is an association anywhere, because we are talking of more than two groups. Can be between group A and B, or group B and C, or group A and B, or whatever, A and C. So if there are four groups, it can be between any group. So if there's no association at all, it will say there's no association anywhere, you rest your case. But in a situation where there's association, we want to know where the association lies. But before we go into that, let's talk about F distribution. So the statistic in ANOVA is F statistic. So F distribution is just like any other probability distribution. It's a form of continuous probability distribution, just like chi-square, t-test. Just in my, just
not only you.
So yes,
Thank you, sir.
Oh yes, we want to talk about the F distribution. So it's a form of probability distribution. It is the distribution of all possible value of the F statistic. We have already talked about the F statistic. The F statistic is the statistic in ANOVA. It's the statistic you get when you divide the variance between groups by the variance within groups. That's F. So it's like another distribution, but it's unique in its own. You can see example. You see the probability density function depending on the degree of freedom. You remember when we started solving it last week on Thursday. Remember, but there are because there are three levels of variances. We have the variance within, variance between, and total variance. And the F statistic is the division, is what you get when you divide the variance between by the variance within. No, we always say that statistics, all these hypothesis tests, is about division of the variability which you are looking at, which is what you want to find if the difference is significant, divided by the inherent variability which you saw within. So it's the same thing. So the F statistic is what you get when you divide the variance between the group, the variability between the group you are, the either 3 group or 4 group or 5 group we are looking at. And that you can see the difference, because when you do their mean, you see that the mean differ. So you want to see this difference in mean. Is it due to chance alone? So, and that difference is between the groups. So, and that is the variance between which serve at the numerator. While variance within each group is what serve at the numerator. So you remember that because of that, we have two sets of degree of freedom. We have the degree of freedom between and degree of freedom within. So when you have two sets of degree of freedom, you see one is bigger than the other. The one that is smaller is the one between, because the one that is bigger will be with the one within, because that one talk about the because we have, so what you get now depends on the sample size of each. You know, for each of them, it's going to be 1 n minus 1, n minus 1, n minus 1, and add it together. But for the one between, it's going to be the number of the group. If you are dealing with 4 group, minus 1. If you are dealing with 3 group, minus 1. Can you see? So look at this graph, and you see that, look at the first graph. You see D1, 1, D2, 1. It's talking of the different variances you are dealing with. Can you see now? So you have two variances. For each graph, guys, variance, and sorry, yes, you have two variances and you have 2 degrees of freedom. You have, because it's 2 levels of variances you are actually testing. So, and each of them has its own degree of freedom. That is why in the F statistic table, we have the 2 degrees of freedom. It's where both of them meet. That's where you find the critical value. So you can see, and one thing also, just like any other probability density function, as the degree of freedom increases, you see as the degree of freedom increase, the F statistic, F distribution begin to approximate normal distribution. So we will not talk much about that because just for you to have a clue about that. So the characteristics of the F distribution, the curve is not symmetrical but skewed to the right. Just like chi-square is skewed to the right. There's a different curve for each set of degree of freedom. Yes, then the F statistics is greater than or equal to 0. So it's like chi-square, there's no negative side. You know, unlike T and normal distribution, which is Z distribution, we have negative side, we have positive side. The chi-square F distribution, there's no negative because it's skewed to the right. So it's starting from 0. Then as the degree of freedom for the numerator and for the denominator get larger, the curve approximates normal distribution. So the F distribution is used in many cases for the critical region, hypothesis testing or test, and in determining confidence interval. 2 common examples are ANOVA, the one we have demonstrated, that is analysis of variance. We also use it not only for that, to show if 2 variances are the same. Can you see? Because even the ANOVA itself is, though it's not comparing the 2 variances are the same. Well, somehow it's dividing one variance from the other. It's dividing 2 variances. Of course, if they are the same, there is no difference. Of course, you will expect the it to be statistically significant if the numerator, the variant, the one that serves as numerator, is far bigger than the one. So if 2 things are the same, we divide it, we give you 1. So ANOVA is the first one. Then F test, which is, you remember 11 tests when we are running these, when we talk about t-test, we talk about 11 tests to test for homogeneity of variance. So it's form of F also. It's to determine if the variance of 2 populations are equal. So those are the 2 usefulness. If you look at it, you see, look at the statistical table for it. You see denominator degree of freedom, that's the one that is along the row, while numerator degree of freedom, that is along the column. So can you see now? So if you want to know the critical value, you have to know degree of freedom for this one, degree of where they meet, that will be the critical value. So now let's talk about that F ratio. So okay, is it F or Planck contrast here? So well, let me just because I just plan to talk about the Planck. Let's just say something about Planck contrast or post-hoc test, because to me that Planck contrast, I don't just want to be talking unless if you are delving into some advanced concept. Because what I just want us to know is that by the time you carry out your ANOVA and it's significant, where does the difference lie? And that is where you either do 2 things. You either do what is called Planck contrast or post-hoc test. So we just say something, so we'll move on to the post-hoc test, because that's the one that is commonly being used. F ratio tells us only whether the model fitted to the model account for more variation and extraneous factor, but does not tell us where the difference between groups. What is just a grammar? It's just saying that you find a difference. It tells you if there's a difference. It doesn't tell you where the difference lies. There are 2 ways to contrast the difference group without inflating type 1 error rate. You know, remember, The reason for not pairing them and testing them like using t-test is because of family-wise error. You are likely to increase the error type 1 error rate. Rejecting one non-hypothesis where it is true. That is your p-value. That p-value. So you'll be thinking you have set your p-value at 0.05, whereas when you do more than many tests at the same time, actually is higher probability you are rejecting it, even though it was set at 0.05. We have demonstrated that. That is a layman or simple way of just understanding is that if you do too many tests at the same time on a particular data set or for a particular thing, too many tests, the probability, even when there's no difference somewhere, the probability of finding different will be is higher. It's high. It's like if somebody does not, especially somebody is good to at least minimum level of F academic strength, the person should pass. That's it. The person should pass. But if somebody said that he doesn't have the required skill and knowledge, if we continue doing the exam over and over and over, means that the probability that one day will just pass does not mean they has improved. But of course, because he's doing it more like gambling, you may pass. It's the same thing when you do too many tests. The probability that one is significant when there's no significant anywhere is very high. And that's the logic behind that family-wise error. So in order to, you see what they do in plan contrast or post hoc test is to see pair them somehow, and now do it too well. But there's a way they have adjusted so that family-wise error will not be there. So the first one is plan contrast. Contrast just means plan comparison, breaking the variance accounted for by the model into component part. Then we have post hoc test. This one is comparing every group using a strict acceptance criteria so that family-wise error does not rise. So we want to skip the plan contrast because unless we are talking of though I've given the lecture workshop when we talk about advanced statistics, but to me it's not so. I will not track people's brain. Those are the slide on it. I want to go straight to what is more important that people want to know, that is good for you to know, that is being used. People don't use it much, but on a few occasions. So let's talk about post hoc tests. I think I'm seeing, yes, contrast, post hoc procedure. This post hoc test, so these are pairwise comparisons that are designed to compare all different combinations of the group. That is, we have 3 groups now. For this one, we have solved the issue of the video, the one we started discussing. There are 3 groups. There are 3 ways you can pair 3 things. If they are A, B, C, A and B is a pair. A and C is a pair. B and C is a pair. So we pair them as if you are doing t-test for each of them pairs. You have adjusted for that familiar. So pairwise just means that you pair them as if you are doing t-test. They are used when you are interested in exploring the data for any between group difference between mean that exists. So where pairwise comparison control the family-wise error by correcting the level of significance for each test such that the overall type 1 error rate across all comparison remain at 0.05. It always change it because they have already, the formula they just adjusted, just adjust. So there are several ways in which pairwise error can be controlled. The most popular and easier way is to divide by the number of comparisons to ensure that the cumulative type 1 error is below 0.05. This method is what we call Bonferroni correction. So what you do is if you do 3 tests, you now divide the probability of doing type 1 error, committing type 1 error there by 3, so that you slash it. But by that you go to see that people, you see that some people now criticize Bonferroni that that method overcorrect. So there are different procedures. So even in SPSS, there are about 18 that they know, many people, many statisticians that make correction to 18 post-op procedure that are listed there. Even if you want to run it, to give you out like this. Look at it. You have this one, the first 14. You say equal variance assumed. That if you assume that it's homogeneity of variance, you use any of them. Then the remaining 4, equal variance not assumed. So those names you see, the most are the name of those people that devise those things. Von Ferroni correction, that's the first one we say. Least square difference. Then, no, that least square difference, just the logic behind is not the name of that person. We have Sigler, Sheffer, Ryan, all these are the name of those people that describe it. Then we have Tamhain, Donnet, Gensowe, and Donnet. So let's see the way. So the logic into the way you how do the correction is now, apart from the conversion that you just divide by number, the value. And the funniest thing that you know that even when you are doing statistics with hand, you cannot calculate p-value with hand. It's only this method, Pisha, but Pisha is P directly. There are just some factorial, one rigorous calculation like this. So you don't calculate, you just know that, okay, this thing at the level of, at a particular level of degree of freedom, this one will be less than, p-value will be less than 0.05. But programming using computer will give it to you. So let's see the way the output, when you run it with SPSS, let's see the way the output is. Let's see. You will see this output now. You remember we have three levels for the data we used last week on the libido. We have the group 1 placebo, 5 of them. You give them placebo. It's not active ingredient. The group 2, you give them low dose Viagra. Group 3, high dose Viagra. Now, you will see the first column in this row, you see I. That is, it tell you about those, which group or dose, because that group is dose. So which group? You see, group 1, group 2, group 3. So you see the second column, J. It means the same group, that is the group you are pairing that one with. So can you see the first one, group 1 placebo pair with low dose, placebo pair with high dose, or low dose pair with placebo, low dose pair with high dose, or high dose pair with placebo, high dose pair with low dose. But you know that the pairing is actually 3. This pairing the computer did now is 6. And the reason is because the computer is not human being. It's just for you to, you have to program. So there's redundancy. For example, when we use placebo low dose, it's the same thing as low dose placebo in the second something. So it's just like, okay, first of all, place each of them. Each of them, if you are doing the first group, you pair with any other of the 2 groups. So if you do it for each of them, that will be redundancy. So placebo stroke low dose is the same thing as low dose. Placebo stroke high dose, same thing as high dose stroke placebo. When you have low dose and high dose, the same thing as high dose and low dose. Can you see now? So you will see the result will be the same, but that's just the way to do it. There will be redundancy. It's the same thing coming when we run correlation. There's the computer, there will be redundancy, because that's the only way the computer can present the work. It's only human being. There's something, you know, a program is programming. So whatever you ask them to do, so they cannot think. So look at it. You will see, I want you to look at something. Okay, look at this SIG, the p-value in what do I call it? In SPSS, the p-value is not denoted as SIG significant. SIG. Look at where is the significant now. Where does it? Which one is significant? You see, placebo low dose is 0.845. Placebo high dose 0.025. Low dose placebo 0.845. You know, it's redundancy, repetition of the other one. Then low dose high dose is 0.196. Then high dose placebo 0.025. Repetition of the other one. And the high dose, low dose 0.19. If you look at the significance, you see there are actually three they repeated on 2 occasions. Can you see? So it just telling you that there are 3 things combination you comparison you do. Just repeating it. A and B and B and A mean the same thing. So now you will see that it's only one that is significant. The only significant is that 0.025, that's the only one that is less than 0.05. The other one is 0.845 and 0.196. They are not significant. You see, they are not significant. So we use this method, we use Benferroni. It's Benferroni we use. Can you see now? Without Benferroni now, is only what is telling us is that the significance is in between placebo and high dose. That is, the only difference you can see in the performance or in the libido is when you are comparing people that didn't take it, which is the placebo, they didn't take any drug, and people that take it high dose very well. So if you look at between low dose and high dose now, it's not significant. What is telling you, there's no difference between someone that didn't take, maybe take 1 tablet, and the other one that take 2 tablets. So even though there maybe there is difference in their performance, is not statistically significant. No much different. But you can see difference between the person that didn't take it and the person that took high dose. So it's the same thing. Between placebo and low dose, there's no difference. Between high dose and low dose, there's no difference. There is only between placebo and high dose that you get a difference. And other thing I want you to understand from here is that you look at the 3rd column, mean difference. So it's trying to remove the mean of each group. You know, look at it now. L minus J is trying to tell you, the placebo, low dose, placebo, high dose. It tries to, if you look at the first one, placebo, low dose, you see the mean difference is -1. If you look at low dose placebo, the mean difference is 1. It's the same thing. One is minus, one is negative, positive. One is positive. Then look at placebo and high dose, minus 2.8. High dose and placebo, 2.8. The same thing, if you see low dose and high dose, minus 1.8. High dose and low dose, 1.8. So that 2.8, 1.8, what are they? If you remember, for the group 1, which is placebo, you remember the mean of the group is 2.2. For group 2, which is low dose, the mean, you remember, was 3.2. And for the mean high dose, the mean was 5. So when you say placebo and low dose, you are looking at difference between 2.3 and 2.2. It will be 1. Because this first one is negative because you are removing low dose from placebo. You are removing low dose from placebo. You are removing 3.2 from 2.2. It gives you -1. Where you say low dose and placebo, which you are removing 2.2 from 3.2, it will give you 1. So it depends on which one. You see, 3 minus 2 is 1. 2 minus 3 is -1. No? So it's the same thing. If you look at the placebo and high dose, you see 2.8. You know the mean for the placebo is 2.2, but the high dose is 5. When you remove 2.2 from 5, it gives you 2.8. And that's why I said that minus 2.8 or plus 2.8, depending on which one you remove from the other one. The same thing, that 1.8, low dose and high dose. Low dose and high dose. Low dose 2.2 and high dose 3.2 rather. Low dose 3.2 mean. High dose is 5. When you remove 2.2 from 5, it gives you 3.2 from 5, it gives you 1.8. Either minus 1.8 or plus 1.8, depending on which one you. Can you see now? So it's the same thing when you now come, we have talked about interpreting confidence interval. It's the same thing. When you now come to the last two columns, the confidence interval, that's different. So if we look at it now, the one that is significant is between placebo and high dose. And it's only that confidence interval that has not crossed 0. Look at it. Between placebo and high dose, it says it gives you ranges from minus 5.27 to minus 0.33. Minus to minus. It does not cross 0. But that is where you remove high dose from low placebo. But if you come to high dose placebo, where you remove placebo from high dose, it will give you positive direction, 0.33 to 5.27. Neither of them cross 1. But if you look at the other, it will start with minus and end with negative. All those other that are not significant between placebo and low dose, it will start from minus and end as plus. So, well, don't bother much if it's gradually you understand. Now, because, what do I call it? That, we know this one now, we use Benferroni to correct. Many people have criticized Benferroni. They believe that it overcorrect. So there are many other, there are 18 that say that even available even in the SPSS, 18. It's possible we have other people that have done, these packages. What they do is that they employ statisticians that will tell them different ways of making all these things. So they will program them. So if we look, there are other options like LSD, least square difference. We have Games-Owen. If you remember, if you go back to where I listed them, can you see? LSD is the second one after Benferroni I listed. Then Games-Owen is one of the one equal variance assumed, number 3 in the second group, Games-Owen. So if I now put DD3 to do LMC, Benferroni, and Games-Owen to see. So all this thing is the same thing in the previous table. I don't need to be explaining everything, but what the difference I want you to see here is that it is significant. You will see that if you remember Benferroni, the one in the middle, we say it's only 0.025 that's significant. But look at LSD, even though it's still the only one that's significant, but it's more significant between that placebo and low dose. If for Benferroni, it gives you 0.025, the p-value, while for LSD is 0.008. You see, the probability of making type 1 is smaller, so it's more significant because it's far, far less than 0.05 than this 0.02. So if you now look at for Benferroni, the relationship between low dose and high dose, we say is 0.1946, but here for LSD is 0.065, almost significant. It's just for you to reduce small, will have reached 0.05. So that shows that something that may not be significant with Benferroni, if you use LSD, it will be significant. So can you see now? That is why, because they have said that LSD overcorrect. If we look at Games-Owen, look at the same thing. It's only that it's not as this thing. Games-Owen, it shows that it's the same thing, but that one is less significant than Benferroni. But mind you, in that system, you have equal variance not assumed. Equal variance not assumed. Look at the p-value is 0.039, and the other one is 0.185. So what I just want you to take away is that you see LSD now, if something was not significant, maybe you do your analysis and you cannot find the different, and you have already, you cannot find where the different lie. And whereas you have already done, you have found a different before. So all you need, and you now see that you cannot see it, where does it lie? So you may have to use something like LSD. I remember I was giving the workshop on statistics in Port Harcourt. There's a PhD student. When I explained this, he said, no wonder. When he was doing a PhD or doing this analysis, and the use Benferroni, he didn't find anything. He said the supervisor said, go and use least square difference. go and use LSD. When she used the least square, she was able to find the difference because Bonferroni has overcorrect. So our advice, if you are running your analysis, it's better you even actually use LSD, least square difference, to find where the difference lies. So here is just a picture, just to, some of this is just for you to understand the concept. There's no big detail. You see, it's the same thing now. You just try to plot. Look at it. Let's say we are plotting the libido along the vertical, the participant along the horizontal. You know that those ones that, for the mean, for those ones that use placebo, their value are lower. They are the green. Can you see? These are the different values. The one that is 3, 2, 4, 1, 1. So you remember the mean. Those dot, the green dot, those are the level. And you remember the mean for that group 1 is 2.2. That's why that line is around that, above that 2. But that's the mean. That horizontal line green is the mean. It's around them. So it means that 2 values are above the mean, 2 values are below the mean among the 5 of them. When you now move to the second group, which is it purple now or whatever color, or blue or purple. Now, you see the different value, 5, 4, 3, 2, 2. The mean for that group is 3.2. Can you see? It's 3.2. Above 3, that line. So, and that shows that 2 values have value above the mean, 2 below the mean. The third group is the one in pink. So you see the value are something like 7, like 6, like 5, like 4, like 3. When and 1, 5 also. So the average is 5 for that one. And that's why the line, look at the mean line, is 5. So 2 has value above the mean, 2 below, 1 has value at the mean. Just to show in geometric space how, just to show the reality the way it is, just to plot the graph. Now, you will see that you remember there's a dotted line across. You remember the grand mean, which is 3.47. So that grand mean, that's where the dotted line is, the grand mean. You remember that grand mean, 3.47, is above the mean for the placebo and low dose, but it's below the mean for high dose. Can you see? So you will see also that difference between the mean for the placebo and low dose. You see it's 1. You know, the low dose is 3.2, placebo is 2. So that B1, that's the difference in their level. That's 1. So the difference between 3.2 and 2.2 is 1. That B1. Can you see? Then the difference between, remember, between the placebo and high dose is 2.8. When you remove 2.2 from 5, that's the B2. Where I'm taking you there is that if you look at, so you may ask, why didn't they do the difference between low dose and high dose? You know, it's not there. So, because whenever you are comparing like that, you choose one as a baseline, as a reference. So, if you have chosen the smallest one as a reference, you are comparing the other 2 with it. So, the placebo is the reference. After that is one that has no, is the control. You are comparing each of them with the control, and that's what the researcher does. The placebo is for control. So you compare what is different between that control and low dose. What is different between that control and high dose. So this B1 and B2, if you know, I've already told you before that regression and ANOVA is the same thing. So I will not dabble into that now. We'll just stop the lecture here. So we'll still come when we get to regression. I will visit this data, revisit this data, and demonstrate the same data set, the way we run. If you remember, when you run regression, it gives you analysis called ANOVA, because the ANOVA is part of regression. So it's actually they are the same. So you will see that it's the same thing. Either you run it as ANOVA or you run it as a regression. It gives you the ANOVA exactly the same thing, because ANOVA and regression is the same. They are two faces of the same coin. So when we get to regression, because I cannot demonstrate it for you now, because we have to first of all talk about regression. When we talk about regression, we now come and visit this data and demonstrate that ANOVA and regression are the same. So that's how you get to know where the difference lies. And mind you, it just happened that the difference lies in between only two of the three groups. In substitution, it can even lie in among it. You can see that you may find difference between placebo and low dose, between placebo and high dose, between low dose and high dose, and between yes, between high dose and low dose, placebo and low dose, and between low dose and high dose, placebo and high dose. You can find the difference in all the three. But in this one now, where the difference lies is between the placebo and high dose. So I don't know if there's any question. Yes, any question? Is it interesting or is confusing?
It's very abstract.
Very abstract.
Yes, sir.
With also of this
illustration. Very interesting.
Yes.
Yes.
But you know the logic between statistics, understanding statistics is when we do lecture like this, we have the explanation. It's good to read something about it also. We do. Like me, the way I learned the statistics, read and do it. Do it, read it, do it, read it, do it. No, sometimes some people come with analysis, and you have to now read about it. How